In number theory, the fundamental theorem of arithmetic, also called the unique-factorization theorem or the unique-prime-factorization theorem, states that every integer greater than 1 either is prime itself or is the product of prime numbers, and that this product is unique, up to the order of the factors. For example, 1200 equals 24, 31, 52 equals 3, 2, 2, 2, 2, 5, 5 equals 5, 2, 3, 2, 5, 2, 2 equals etc. The theorem is stating two things: first, that 1200 can be represented as a product of primes, and second, no matter how this is done, there will always be 4 2s, 1 3, 2 5s, and no other primes in the product. The requirement that the factors be prime is necessary. Factorizations containing composite numbers may not be unique. This theorem is one of the main reasons why 1 is not considered a prime number. If 1 were prime, the factorization would not be unique, as, for example, 2 equals 2a, 1 equals 2a, 1a, 1 equals. History, Book 7, Propositions 30 and 32 of Euclid's Elements is essentially the statement and proof of the fundamental theorem. Proposition 30 is referred to as Euclid's lemma, and it is the key in the proof of the fundamental theorem of arithmetic. Proposition 31 is derived from Proposition 30. Proposition 32 is derived from Proposition 31. Article 16 of Gauss' Disquisitions Arithmeticae is an early modern statement and proof employing modular arithmetic. Applications. Canonical representation of a positive integer equals, every positive integer n greater than 1 can be represented in exactly one way as a product of prime powers, where p11 is the product of prime numbers in two different ways. We must show m equals n and that the qj are a rearrangement of the pi. By Euclid's lemma, p1 must divide one of the qj. Relabeling the qj if necessary, say that p1 divides q1. But q1 is prime, so its only divisors are itself and 1. Therefore, p1 equals q1, so that, reasoning the same way, p2 must equal one of the remaining qj. Relabeling again if necessary, say p2 equals q2. Then, this can be done for each of the m pi's, showing that ma per mole currency n and every pi is a qj. Applying the same argument with the s and s reversed shows na per mole currency m and every qj is a pi. Elementary proof of uniqueness equals, the fundamental theorem of arithmetic can also be proved without using Euclid's lemma, as follows: assume that s greater than 1 is the smallest positive integer which is the product of prime numbers in two different ways. If s were prime then it would factor uniquely as itself, so there must be at least two primes in each factorization of s. If any pi equals qj then, by cancellation, s pi equals sqj would be another positive integer, different from s, which is greater than 1 and also has two distinct factorizations. But s pi is smaller than s, meaning s would not actually be the smallest such integer. Therefore every pi must be distinct from every qj. Without loss of generality, take p1,